We are going to now talk about gas substances. We haven't really focused on it before. In this video, we're going to talk about kinetic molecular theory. This is your learning target. Now, before we talk about gas and the behavior of gas, I'm going to use a simulation, and the simulation is from PhET. And on the left side of the screen, I have some questions that I want you to think about as I take you through the simulation, okay? So the 4 questions I want you to think about is: how would you describe the activity of the gas particles in the container? How does the volume of one gas particle compare to the volume of the container? What happens when the gas particles collide with each other and the walls? And finally, what happens to the movement of the gas particles as the temperature increases? And what happens to the movement of the gas particles as the number of gas particles increase? Now, you can probably look at the simulation and already predict what's going to happen. So actually what I want you to do is pause this video, and as you look at the simulation, go ahead and just try to predict some answers, okay, just by what you see. So let's start with the first question. How would you describe the activity of the gas particles in the container? So these are the gas particles inside, and how would you describe it? How are they moving? Do they stop? Are they moving in waves? Are they moving in circles? Are they moving in straight lines? Are they moving slowly, quickly? Or do they just stay at one spot? Or are they free to move around? So if you take a look at what's going on here, first of all, you'll notice that they are free to move anywhere and everywhere, right? They are touching the walls of the container. They are bouncing off each other. They're not moving in waves. They're moving in straight lines. You can see that as they bounce off each other or bounce off the walls, they then move in the other direction, not necessarily the opposite direction, but just in a different direction, right? And they're constantly moving. They never stop. So question 2, how does the volume of one gas particle compare to the volume of the entire container? Now remember, volume it means space, right, or size. So the size of the gas particle is extremely small compared to the size of the container, right? Number 3, what happens when the gas particles collide with each other in the walls? We talked about this, actually. We said that it keeps moving. It doesn't stop. Once it hits each other, once it collides, it just moves in the opposite direction, or in another direction, right? And last question, what happens to the movement of the gas particles as the temperature increases? So I want you to take a look at what's going to happen with the individual particles, okay? And I want you to actually look over here at the pressure gauge, okay? So right now it's bouncing back and forth between 45 to 46 atmospheres. So if I were to increase the temperature, so I'm going to heat it up, what do you see happening to the movement of the particles? If you said that they're moving faster, you are absolutely right. And what do you see happening to the pressure? The pressure also increased, right? Do you think that there is a relationship between how fast they're moving, or the collisions that are occurring, and the pressure? Think about it. Okay, let's answer the last question here. What happens to the movement of the gas particles as the number of gas particles increase? So I kind of reset the simulation here. The pressure is now back down to, again, going back and forth between 17 and 18. And what do you predict is going to happen if I were to add more gas particles? So let's pump in maybe 3 more pumps, and you see that as the number of gas particles increase, what is happening here? They're bouncing off each other more, they're bouncing off the walls more, their movement is increasing, right? And what do you see happening to the pressure? it went up, right? It went up to 38, 39, 40. So what do you think is the relationship between pressure and the number of collisions? If you said the more collisions there are, then the more pressure that's created, you're absolutely right. And that's what we're going to get into right now. So let's talk about the characteristics of gases, the behavior of gas. Okay? Gases expand and compress to fill any container. So taking you back to the simulation, if I were to change the size of the container, the volume of the container, so if I make it smaller, you can see that the gases are compressing to fill the container. And then if I make it bigger, again, the gas particles are now expanding to fill the container, right? And we see that there is random motion, right? You can't really predict where the gas particles are going to go. There's no attraction. They're not sticking together, right? There's no attraction there. There's no volume. It's lots of empty space. The gas particles itself is extremely small compared to the size of the container. All gases exert pressure. And we talked about how pressure is created by these collisions, the collisions of these gas particles on each other, and the collisions of the molecules with the walls of the container. And that is how pressure is created, okay? So more collisions, more pressure. Less collisions, less pressure, okay? So keep that in mind. The magnitude of the pressure is related to how often and how hard the molecules strike the wall and each other. Now, this is known as the kinetic molecular theory. The kinetic molecular theory describes the behavior of gases, and there are 5 points to this theory. 1, gases are composed of molecules whose size is so small, negligible, compared to the average distance between them. 2, molecules move randomly in straight lines in all directions and at various speeds. 3, the forces of attraction or repulsion between two molecules in a gas are very weak because gas particles are far apart except when they collide. So really, these gas particles, they don't attract each other and they don't repel each other, okay? Because they're so far apart, and the only time that they're close is when they're about to collide. When molecules collide with one another, we call these collisions elastic. Elastic means no kinetic energy is lost. And lastly, the average kinetic energy of a molecule is proportional to the absolute temperature. So this means that if we were to increase the overall temperature, then the overall energy will increase. If we were to decrease the temperature, then the overall energy of the gas will go down. Now, we're going to get into the math part in our next video. And so we're going to talk about 3 important units. Pressure, which we actually started to talk about in our previous video. When we talk about pressure, we're looking at the units ATM, atmospheres, torr, kPa is kilopascals, and mmHg is millimeters of mercury. Now again, there's different pressure units. You know, if you have ever worked with your tires before, that's PSI. It all depends on the type of equipment that we're using, okay? Now at standard pressure, we're talking about 1 atmospheric pressure, 1 ATM. Remember, that's the pressure at sea level, okay? So when we say standard pressure, these are the numbers and units for standard pressure. So when I say standard pressure, I'm talking about 1 atmosphere, or I can say 760 torr, or standard pressure is also 101.3 kilopascals, and standard pressure is 760 millimeters of mercury. Okay, so this is something that you should know. So again, this should look familiar, the standard pressure, because we talked about it with our vapor pressure diagram, right? The second unit that's important is volume. When we talk about volume, we want to go ahead and convert our volume to liters, okay? So keep in mind that there's 1,000 milliliters in 1 liter. So for example, if I have 2,091 milliliters and I want to convert it, I'm going to set it up using the fence because that's how we've been doing it. So I start out with 2,091 milliliters, copy the milliliters, put the liters on top, put the numbers where they're supposed to go. 1,000 milliliters is equal to 1 liter. Okay, so that's why I put the numbers there. Like units cancel out. In this case, I'm going to go ahead and divide, and that's 2.091 liters. Okay. Another example, if I have 435 milliliters, again, setting it up, I'm going to bring the milliliters down, liters up top. Like units cancel out, so again, you're going to divide, and that is equal to 0.435 liters. Okay. So everybody understand how to convert from milliliters to liters, right? The last unit that's important to us when we're talking about gases is temperature. Now, standard temperature, we're talking about Kelvin, and this is called absolute zero, okay? So 0 degrees Celsius is equal to 273 Kelvin. So you'll notice that we will never be dealing with negative temperatures, especially because we'll be converting our Celsius to Kelvin, all right? So for example, if I have 50 degrees Celsius, the way that I'm going to convert this to Kelvin is 50 plus 273, and that's equal to 323 Kelvin. It's as simple as that. Another example, if I have a negative Celsius, right? Negative 25 degrees plus 273 is equal to 248 Kelvin. Okay, so all you're doing for temperature is adding 273, because when it comes to gases, we are always looking at Kelvin. We're not talking about Celsius. We don't want Celsius when it comes to gases. Okay, so in the next video, we're going to look into all the different types of gas laws and look at the relationships between these variables.